Hello, everyone. I'm making this video to provide the solutions for your midterm. So in this midterm, I ask you to answer 3 questions. The first question is really just some book work. Just to remind you, the first question asks you to write down all 4 thermodynamic potential functions in a differential form. And then ask you to extract the Maxwell relations. So these are really standard material, so I won't spend time on this. So basically for this question, for question 1, which is this simple question, as I say, you need to remember something. And for this course, it would be reasonable to ask you to remember the definition of du, and then to understand how to get the other potential functions, for example, the enthalpy, the Helmholtz function, and Gibbs. So this is basically for PVC system, you don't really have much to memorize. You just have to understand how to get all these different combinations to get the natural variables you want. So I will start from question 2. And another reason I want to make this video is because question 2 about the ideal gas and question 2 about this problem I show you, mainly about the ideal gas and the entropy, should remind you of something we are doing in statistical physics right now. And also the next question, Q3, about photons, there is something that will be very useful to learn in thermodynamics as well as in statistical mechanics. We are going to, in the remaining lectures, we are going to analyze the behavior of photons again. So it will be very nice if you could spend time to watch this video as soon as you can. Okay, so let's begin with Q2. So this is a question which asks you to play with thermodynamics, but with a very specific form of the internal energy. So by now, after handing in all this assignment 8, it shouldn't be too surprising to you that for monatomic ideal gas, you can derive a very specific form of the internal energy here in this midterm. Of course, you didn't know, you probably didn't know this result, so I gave it to you. Okay, so this is a specific form of the internal energy for monatomic ideal gas. And question 1 asks you to use the first law to show this result. So for reversible adiabatic process, you get this result. All right, so how do we do this? So for A, you use the first law. You first write down the equation you need. And this is adiabatic reversible. So the first term is 0. And then you have your PDV. Okay, so you only need to deal with du, which is PDV. And du, you can just differentiate this, right? So du, so what you are left to do is to write down du. So du is d times, you need to do the differential for this, nkbt, and this will be it will be minus PDV. But if you realize something useful about this question, namely you are dealing with an ideal gas, you can save your life, you can save your time, and you can make your life simple. Okay, so what do we do before we move on? We know this is an ideal gas, so you know the equation of state for the ideal gas. So nkbt is PV. Okay, so you equate this to the right hand side of this equation at the top. This whole thing is minus PDV. So you are ready to you are ready to manipulate this. Now this is very simple. You don't have temperature coming into play. You just have a PV on the left and PDV on the right. Okay, so let's do the differential. We will have 3/2 PDV plus 3/2 VDP. Okay, we can move this to the other side. We have this. Okay, and you basically get the answer you want. You just rearrange a bit. You can combine PDV and 3/2 PDV, and then you have VDP on the other side. So that will give you a 5/3 dV divided by V, volume, and there's a minus sign. Huh? Don't forget this. So this is P dP divided by P. And then you integrate from process 1 to process 2. You integrate from 1 to 2, and that will give you your solution. You get your PV, P1, V1 to the 5/3 is the same as P2, V2. Okay, and that is the desired result. Okay, so this is A. And B, you are asked to show for this system we just talked about, you have this result. So I think maybe the best thing to keep in mind is this line here. If you keep this this result, it will be really useful for the rest of the question. Okay, so let's look at question 2. Question 2, you're asked to find the entropy change. So again, this is for your. I will just first write everything down for you. So this is the first law divided by t, and you have a reversible reversible process here, and then you can immediately relate this to entropy change. So this is a reversible process, and this is the entropy change, du minus minus PDV divided by T. Okay, so your ds is 1/T du. Okay, what is my du? You go back up here, du again. You see, I want everything in P and V, so this is the most useful form. So du, I will just plug in this result right away. And then and then what I have remains is P divided by T dV. Okay, so here you see you have 1/T, and you have PDV again. So that can be combined with this. Okay, so please try this yourself. You just need to do the product rule carefully. So you get this result, 2 terms. You get the one with dV and then the one with dP. So the one with dV is like this. The one with dP, you don't have another term to combine. So there will be 3/2 V/T dP. Okay. And now you can use your ideal gas equation of state again to rewrite this P/T and this V/T. You will get so this is using the ideal gas result, and you will get this line right away. Okay, so you get the end result is this. You get NKV dV/V, right? So this is P/T is NKV divided by V. Okay, and the V/T, you can also get something similar. You get NKV dP. Okay, so this is using the ideal gas equation of state. All right, so what is the next one? The next one is to show that the change of entropy is this. Should have so the next one, let me erase this. So C. C, you're asked to show the change of entropy. Okay, so that is actually you can do it even without getting your B. Okay, so you take B delta S, and that is from 1 to 2 ds. Okay, and delta S is defined like this. Okay, so this is kind of important. So this is you can see as S2 minus S1. So everything with 2 is the final state. Everything with 1 is the initial state. So keep this in mind. Otherwise, you always need to know which one is the final, which one is the initial, in order to get the sign correct. Okay, so what do? We go back to B and take this equation here. So we have 5 half NKB. So this is 1 to 2, right? So you have dV divided by B, 1 to 2. This is V1 to V2. And then you have this NKB, 1 to 2, dP divided by P. Okay, then you have a bunch of logs to deal with. There will be a NKB. Now you can see all these exponents here. So those are related to this prefactor. So you know you have done something right because you introduce log here. Okay, so you have log V2 divided by V1. And you have this prefactor here. I'm going to put it in right away. Okay. And then for the pressure term, you have the same. So I'm going to square bracket this. So for pressure, you have P2 divided by P1. And then you're going to raise to the exponent power of 3/2. Okay. And now you tidy everything. You have the log, you tidy everything. You get this result. Okay. Now, this should be reasonably straightforward for all of you. I think some of you gave very messy answer. That's because of this line here. If you fail to realize this, you will have a lot of more symbols to manipulate. Something that is less satisfying is this question. This is 4. This one we already deal with. This one. This one is about getting the this exponent, this C as a function of n. This is related to what you are learning now, the Sacru-Tetrode equation. Were you asked to do? You are asked to use this property to derive this result. Okay, you're asked to use the fact that the entropy is an extensive variable, and you're asked to show this. So the way to show this is the following. You look at it here as, and then you see how to manipulate the system size. You can use you can imagine make say lambda copies of this, or for simplicity I would just make something a little bit more transparent to probably to some of you. I'm going to double the system size. I'm going to take this system and make an identical copy. That's to say, I double the volume, and I by doing so, I naturally double the number of particles. Okay, so if I do it this way, what happens? What happens is I will also double the entropy. Okay, so this will be the original copy. And if I make the system size double, then the entropy has to double. So this is the key equation that you need to realize, and the rest is kind of simple. Okay, this is a bit actually very similar to the case of this Sacru-Tetrode equation, where I show you if you use the wrong single particle partition function, a wrong relationship between the single particle partition function and the system partition function, you get something very strange. And what is strange? In the lecture, I already told you this is about the property of the entropy. Okay, so now coming back to the midterm, what do? You use this equation and plug in all the result. Okay, let's try. So when I see n, I will replace by 2n. When I see pressure is intensive, I cannot do anything, so I will let. Volume is double, so I will have 2v, like that. Okay, and don't forget this is a function of n, so I will now have to double that too. I don't know this function yet. This is a point you are asked to do it, to find it. Okay, and then this is the same as 2nkb. Just copy everything. Log of p 3/2, v 5/2, and this. Okay, and you realize you have a lot of nice cancellation. This 2nkb is gone, and everything here you have p to the 3/2. This one will be gone, and what remains will be this. So what remains will be, you have this log of, now this v will also cancel this one. So what remains is this. You have 2 to the 5/2 c of 2n. This whole thing will be the same as log of 1 over c n. Right? All right. So you have tidy a little bit. You have this result. 2 to the 5/2 c to the n. Okay, and remember, what is this 2 here? This is you can trace it back. This is related to the fact that I double the copy. If I make it 3 times the size, then this, it will become 3 to the 5/2, and this of course will become 3. And you can now readily show that this is compatible to the form I want you to show. Namely, if you take Cn to be this, some unknown constant, you can get this result. Okay, so that is the answer. Okay, so what is next? The next is E. This question asks you, this is a big question. It's related somehow to the form of entropy we derived earlier. Okay, so now one, write down the definition of enthalpy. And this is a bit like giving you a double point, because you already deal with this earlier, okay, in question 1. So you already gain a bit of points here, and now I give you a little bit more. Okay, 1, enthalpy. Okay, this is a form of enthalpy, and express this explicitly for our problem of monatomic ideal gas. Okay, again, it's important to realize U can be written as 3/2 PV, and then you have this PV, and that's it. Okay, so enthalpy is also very simple, very explicitly given in terms of PV. And 2, now use the fact that H is a conserved quantity in the process. We showed this in the lecture, but now I just give you this fact. Find the expression for the change of entropy. So this delta S is S final minus S initial. So everything labeled with 2 is final. Everything labeled with 2, and everything labeled with 1 is initial. Okay, so keep this in mind. So I want the final minus the initial. And in fact, you just use the equation derived here, this one, right? This is also delta S. You just use this one. All right. So let's do it. But the only thing you need to be careful is this business of 1 or 2. All right, so that equation tells you you have if you have 2 minus 1, so 2 is the final. It has to come upstairs of this ratio, this fraction. Okay, this is 1. 1. Okay, this is the equation that you could copy from in the exam from previous question. All right, so I have nkb, I have log, and now I want to use the fact that this is a conserved quantity, which means I will have 5 halves P1 V1 is the same as 5 half P2 V2, which means P1 V1 is the same as P2 V2. So I will have a lot of cancellation here. All right, so I would do it like this. Now, I want to express this in terms of PV, and you realize you can write it like this. I will do the top, and the bottom will be equivalent. So you can the top can be written like this. Okay, so V is raised to the 5 halves. That's correct, and P2 pressure is raised to the 5 half minus 1. And that is to say you raise it to 3 halves. Okay, so this is correct. And then I have P1, B1, 5 halves, P1, like this. Okay, now you use the fact that enthalpy is conserved and enthalpy is proportional to P times V. You can cancel this. Yeah. Okay, so you are left with this expression, which is very similar to the case of Joule expansion I derived in the lecture. There we talk about volume, here we talk about pressure. And now you probably can convince yourself why I told you this process, this Joule-Thomson process is not reversible. Okay, why this is not reversible? That is the next line here. Okay, so now if this now the system is thermally isolated from the environment, so the change of the entropy for the universe is the same as this delta S we just calculated. There are two ways to there are different ways to argue about this. Here, you are asked to show that the final pressure cannot be higher than the initial pressure. Just like the case of Joule expansion, you are asked to show about the final volume has to be larger than the initial volume, and you cannot have the Joule compression. Okay, so this is the application of the second law again. So this change of the entropy must be greater or equal to 0. This is the second law. This is an application of the second law. Okay, so you go back and read this equation. This tells you this whole thing has to be greater or equal to 0. And therefore, this can only be true if P1 is greater than P2. Okay, so P2, after you go through this process, the pressure has to drop. Right, and then now you can imagine if you push it backward, if you push it from 2 to another state, you push the piston on the right to the left, you get P3, V3, and T3, and that will become even lower. The pressure will become even lower. Okay, and that is why this is not reversible. You do not recover when you push this piston back, you do not recover your P1, V1, T1. Okay, so this is a rather well-known experimental fact, and now you are asked to show it. Okay. Next is about this photon. Let me prepare the slide and I will show you that. Okay, about this photon. Now, this is a really fun problem and it's very related to what we are going to do with the Bose-Einstein statistics. Okay, so you are given this. You have a PV system containing a collection of photons, and you are asked to you're given some more effects. So first, the internal energy per unit volume is only a function of temperature. This is not quite the same as the ideal gas. Ideal gas tells you the internal energy is only a function of temperature. So now you have this energy density coming in. Okay, so U, the little u is called the energy density for obvious reason. And you are also told that pressure is related to the internal energy by this relationship. Now, just to let you know, all these result can be obtained by considering the statistical mechanics. So again, these are given to you. And in the usual statistical part, you don't go through this analysis, So this is a good chance to have some thermodynamic preview before we do statistics. Okay, so here, let's begin. A, you are asked to assume this expression is a good description of this system. And this is a fun thing. You are going to do this, and then later you are told to repeat the same thing for an open system. And then let's see whether this assumption is still good. Okay, so keep in mind the purpose of this exercise. And how do you show this? You are given the hints. Okay, you are asked to consider this. So as usual, we will then look at what happens to ds when you have dt and dv. Okay, so then you have a partial derivative like this, dt plus dv constant t. Okay, so this is my first expression. And second, I will also remind you what is the first law. First law, if I written in terms of ds, first law is TdS here, right? So if I just change it to the subject, I will have 1 over T du plus P over V, P over T dV. Okay. So this is the first law. This is from here. You are asked to assume this is valid, and I assume this is valid, and then just rearrange to get this. Okay, we need a little bit more about this expression. So we know U, little u is the energy density. So big U. So this is really the big U. This is a big U. Big U is related to the little u by volume. Right? So energy density, little u is big U divided by volume. And therefore, du will be a little u dv plus v du. Okay. And then I can write it further. I have u dv. I want to use the fact that this u, little u, is a function of t only. So I can change my variable like this. I will have v. Du, I can then write it as du dt. Okay, this is total derivative, not partial derivative. Why? Because little u, is a function of temperature only. Okay. And now from 1, I can rewrite 1. So expression 1 will be ds. And I have 1 over t du. Sorry, I mean 2, expression 2, first law. I will have 1 over t d big U. D big U is what? Is this thing. So it's a little u dv plus du dt plus u v, sorry, p over t dv. Okay, And we have a bunch of cancellation. We have we can simplify it further. We have dv here, and the m is to later to compare with 1. Okay, we write down two expressions for ds. We simplify as far as we can and then change it to the expression we want, little u, and then compare with the first, and that will give you the answer you want. Okay, so let's do it. We will have v over t. So we have this v over t for this term with dt times du, d little u dt times dt. Okay, this is the term with dt. Plus the term with dv, we have u little u over t plus p over t. And then the whole thing is dv. Okay. And now we can compare with 1, and that's it. The coefficient of dt gives me this, right? This is the expression I want. Okay, so I compare the coefficient of dt. I will have this result. And this is the same as this v over t du dt. Okay, and likewise, if I do the rest, there's the remaining one. This thing, the coefficient of dv. So I will have this dv here. I will have little u over t plus p over t. Now this is not quite the form we want, but we know we can simplify a bit more because we know p is related to u.